After establishing the optimization objectives and constraints in our last lesson, the topology optimization has already run. Let's take a closer look at this block, all its inputs, and the information that we see in the results. For now, we'll collapse our optimization objective and our constraints and focus only on the topology optimization block. The input for max iterations is pre-populated with a value of 200. Because topology optimization is iterative, we can set a limit for the number of iterations attempted. For more complex optimizations that may take longer to run, this should help users to reduce computation time with the trade-off of accuracy. Another way to reduce computation time, assuming the same trade-off, is by modifying this minimum objective change. Once the TopOpt iterations converge to within this number, the process is considered complete. Therefore, the higher the minimum objective change, the faster the optimization will converge, and the lower this input, the longer it'll take to run. Minimum density change is another convergence threshold, one that compares the optimized density between iterations. Again, we'll see a slight trade-off between accuracy and computation time. The boundary penalty affects density values at the edges of the design space. An input of 1 will lower the density at the edges, while an input of 0 increases the density. Therefore, lesser inputs will remove more inner material from the part, and greater inputs will remove more material at the edges. Save increment controls data storage and therefore affects file size. An input of 0 will save only the first and last iterations. An input of 1 will produce the largest file size and save every iteration, and any input larger than 1 will be the increment by which iterations are saved. For example, an input of 2 would save every other iteration of the topology optimization. Filter size can be used to indirectly control the minimum feature size and remove the jagged checkerboard artifacts that we see in TopOpt. If left blank, this will auto-generate based on the model size. Initial density can be any value between 0 and 1 to give an initial guess at how the result will look before the process begins. If left blank, this will be set to 0.5. I'll go ahead and create a variable out of our topology optimization, and I'll pull in a translate block so we can view our results side by side with the original part. I'll right-click, make a variable called TopOpt, and I'll pull in our translate block. To translate our initial design space. Viewing these two parts beside one another, we see that a lot of this material from our original part has been removed during our TopOpt process. Since topology optimization works by assigning a TopOpt density value between 0 and 1 to each mesh element, we can use this topology optimization window to get a better understanding of how the calculated densities have affected our part and how the output contributes to our objective. The isocontour option shows the single surface with elements meeting the nominal threshold, which can be modified using this slider. The threshold equals 0, our initial part can be seen, and as it moves toward 1, you see more and more removal of elements with lower TopOpt densities. The iteration slider shows the evolution of the TopOpt through each iteration. The thresholded elements option offers a similar visual representation, but gives a more granular view of individual mesh elements and their TopOpt densities. This can help us to visualize how and where material with different TopOpt densities is removed throughout the optimization. Opening up the settings in the results window, we can control the color palette of our elements, whether the gradient is continuous or banded, and the preferred number of color bands. We've now completed our topology optimization. Next, we'll need to perform some post-processing of our results to generate useful geometric information in nTopology.